Zonal functions, or functions that operate on zones. Remember, zones being logical units of analysis when we have cells that belong to the same categorical category. So we'll look at zonal statistics and zonal geometry, things that operate just on zones. So just recall from lecture 1 in the extended raster model, has the concept of zones. So they only exist in integer level grids and theoretically only exist as a concept in categorical levels of measurement, so categorical rasters. And we can have any cell with a number or a category, even if it's by itself, that's a zone. Most often, though, zones will have many contiguous or discontiguous non-adjacent regions of cells with the same value. For example, here, all the values of 2 equals zone 2. All the values of 4, zone 4. All the values with 5 only occurs there. That's the zone 5. And so it may be, for a number of reasons, that we want to undertake some computations at the zone level. So using all of the cells which are having a single identifying value, unique value. So a zone is composed of all cells in a raster with the same value. They can have several regions, so if they're disconnected, non-contiguous, non-adjacent. For example, there are 2 regions to zone 2. 2. How about zone 4? There are 1, 2, 3 regions for zone 4, because there are 1, 2, 3 sets of cells that are disconnected with the values of 4. So those 3 disconnected things are called regions. 1, just looking at them, I'm counting 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, could have between 5 and 6 regions. And that's weird, right? 5 or 6? How can there be 5 or 6? Well, it depends on whether or not you define contiguity as sharing just a cell corner. Is 1 next to 1 if they just share a corner? If yes, then you have 6 regions. If yes, you have 5 regions. If you consider that as adjacent, so that means they're connected. So that whole thing, that cell, and that cell are one region. So that would be 1, and then we'd have another one here, 2, 3, 4, 5 regions. If, however, you say, no, sharing a corner does not consider, or you don't consider that as adjacent, then that would be 1, 2, 3, 4, 5, 6 regions. So the number of regions can depend on how you define adjacency. By default, sharing a corner is considered adjacent. So by default here, we would have 6 or 5 regions for that reason. Here's a zone example. So so here we have a number of different zones. Remember again, zones here are represented with colors, and each one will flash yellow. So all of those different colors are zones. So some zones have a lot of regions. Like if you look at here, I would say probably the light green and then the dark green probably have the most individual regions comprising them. Whereas this color green over here probably has the fewest number. may have the few, or one of the fewer numbers of regions, because a lot of it is connected together, right? But the dark colored one, the dark forest ones, are probably the most, since they have the most discontiguous cells or regions. So we can have zonal operations that are of two forms, geometry or statistics. Zonal geometry works with groups of zones and works with a single input raster. So you stick in your categorical data into a zonal geometry operation, and it will output computations about the zone, such as the area of each zone, the perimeter of each zone, the centroid of each zone, the thickness of each zone, thickness being the, if we have a zone like that, well, the longest axis in here, axis might be that, so that might be the thickness of each zone. Just using one region here to illustrate that. It's hard with multiple ones to figure that out, obviously. If you have that, this one, which one is the, and that's all one zone, how do you figure out the thickness of that zone? So area, centroid, perimeter, mostly area and perimeter are used a lot with zones, zonal geometry. So you input a grid and it outputs either an output grid where each zone has that summary statistic of the geometry associated to each value in the zone. So one layer might be, you might have one layer and you assign the zonal area to it. In the output, the area of each zone will be assigned to each cell in each zone. So each value or each cell would then have an area value associated with it that belongs to the entire zone, not the cell. In a table, you'd have a list of zones and then values. Zone 1, 2, 3, for example, and the values of area. Something like 800 meters square, 722 meters squared, 36 meters squared, or whatever the units are that you're working in. These are the zonal statistics measures, which you've seen already in the focal function, so there's nothing new here. They're all the same ones. And with the same caveats as to some apply to categorical, some apply to continuous data. Now, for zonal statistics operations, you need to have two things, or two layers. A zone layer that defines the zones, and that could be anything that is categorical. So anything categorical. And a value grid. The value grid can be any raster layer. Usually, the value grid is a continuous. So it's usually going to be a continuous layer, the value grid. So the zone is any categorical layer, and the value any raster layer, usually a categorical one. Then what happens? Well, we would put in the zone and the value grid, which is that grid which is often categorical, but it could be also often continuous, but could be categorical. If it was a categorical one, then we might ask what the zonal variety is. So what is the variety of the value grid cells within each zone of the zonal layer? Or it could be a mean for continuous data. Let's say the value grid was temperature. So we have zone grids might be elevation zones. So we have elevation zones, and then we want to figure out the, let's say, the average temperature. Within each zone, that's what the zonal mean would do. It would output either a table with the zone identifier and then the average temperatures for each zone, or a new raster layer where every zone has assigned to it the temperature value of the average for that zone. So outputs from zonal statistics can be rasters or tables, and you choose. There's a zonal statistics output and then the zonal statistics as table output. So zonal statistics as table is often the most usable or the most used one. And it can be joined back to the zone grid because both will have zone identifiers in them. So you could do a table join of the zonal summaries table back to the zone grid to get access to the zonal summary values. Zonal statistics as grid outputs a new grid with the summary statistical values assigned to each zone cell. There is no common way to do anything with those other than space. So in a zonal output grid, you're usually going to be using that in some computation, whereby you need to know the value of the summary for each of the cells within each zone to multiply or divide by something else. Let's look at an example. So we start with A and B here, or I should say not A and B, but we have two layers at the top. We have first elevation, so that's an elevation layer, and then we categorize it into elevation intervals from low elevation to high elevation, and that's using the slice function of Spatial Analyst. We say we want to slice it, and this is just like if you were to symbolize it, you get the same thing, but out comes a actual raster with the zones, not just a symbolization of it, as you would when you change the colors of the symbology or the number of classes in the symbology for a classified continuous map. So we have elevation, we put it into slice, we say how many classes we want and how we want to divide those. So that could be natural breaks or whatnot. Here I just wanted to use equal interval so that between the minimum and the max elevation, it would take 10 equally spaced values from lowest to highest. That then creates this, which is a zone grid now. So we've converted a continuous layer into a zonal layer by classifying it. Then I also have land use. And I want to get zonal statistics as table. For each of these elevation zones, I want to get the average elevation. So I use the zonal statistics as table. I put in my zone layer, which is always the first one. Then the column that will be used in the zone layer, which is value here. Value, the column value is the 1 to 10, which is the output for the slice function. 1 being the lowest value of elevation, 10 being the highest range of elevation. Then I state what my what do they call that? What do we call that? We have our zone layer and our value layer. Sorry, yeah. So that's also the value. Just drew a blank there for a second. So we have the input zone, and we use the value field. That's going to be the mostly common one used, by the way. And then land use is the value. So we're summarizing a categorical with a categorical here. And then I name the output of the table name, zone tab. And I say data and what the measure is that I want. So data just means as long as there's data within the zone, ignore no data in the calculations. And I want variety. So I want to know how many different types of land uses there are in different elevations. So maybe, because I might have a hypothesis that, well, at lower elevations, I might have more land uses than at higher elevations. So once that runs, it outputs a table. The table has the value, and that's coming from here, 1 to 10, because each slice is going to 10, so I have 1 to 10. 10, like so. So that's in the value. So 1 is the lowest elevation, and then I can see the variety over here. So at the lowest elevation, I have 11 land cover or land use types. At the highest elevation, I have 8. So with 8 at the highest and 11 at the lowest, I can see that maybe there's something here, in that, 8, 9, 12, at these higher elevations, it certainly goes down by a few land uses in terms of the variety of the richness of land use there. In between, though, it's pretty much similar. We get 12, 13, 14, 12, 13, 14. Probably no real relationship here in this region, because we're at a pretty low elevation region, wherever you are on elevation in this region. What if we wanted the average elevation for each land use? So we reverse that idea. So we want to get what, maybe we have a hypothesis or some reason to believe that at different elevations, certain types of land uses, will occur. So at high elevations, land use might be mainly forest. At low elevations, it might be mainly agriculture. So first we have to figure out, well, what the average elevation is for each one of those. So in this case, here, we have two rasters, a land use and an elevation raster that you can see here. That's LUse and LEV. Again, zonal statistics table. Land use is the zonal because it has zones. So it's a zonal data set. And I want land use, that column in the table, rather than value, to be output, since I want to be able to figure out which land uses belong to which elevations, average elevations. I want to see the names of them. So I use that particular column in the land use categorical raster. Then my values raster, elevation, the output will be called zone table, data again, and then mean, since I want the average. And then that outputs a table here where we have land use by name, and we have all of the summary statistics as well. Count how many, that's the total number of cells, and then mean. So for example, so what ones are highest here? I can see that this one, fen, are at the highest average elevation, and at the lowest elevation is open water. Well, that makes sense, since the river would be the lowest elevation in the region. And you could then look at it, sort it in different ways, graph it, and figure out if there's any type of relationship or hypothesis that could be based on that.